Next topic in basic concepts in organic chemistry is electronic displacements in a covalent bond. Electron displacement in a covalent bond, how electron displays in a covalent bond. So first topic under this heading is inductive effect. Inductive effect is denoted, this is represented by a symbol capital I, and this is a permanent effect. This will remain in a compound. An inductive effect is seen in saturated carbon chain where carbon atoms are linked by single bonds. In these compounds, this effect is seen, and it is of two types: plus I effect and minus I effect. Plus I effect, first of all, if a saturated carbon chain will take, and to the end of this there is a electron releasing group here, electron donating group, that is electron releasing group if it is attached. Examples of electron donating groups are alkyl group, alkoxy group, OH group, amino group, etc. These are electron donating group. If this kind of group is attached to the saturated carbon chain, then what this group will do? This will release electrons. This will give electrons to carbon chain. And as a result of this, the electrons from this atom, they are displacing towards carbon chain. So this carbon chain will start getting electrons. So there will be partial negative charge. Electrons move away from this group. So there will be partial positive charge. And electrons are released further to this carbon also. This also gets some negative charge, and the third carbon also gets little bit of negative charge, and we'll show it by using the arrow, that is electrons moving towards carbon chain. And this effect will cease after 3 carbon atoms. So this will remain only till 3 carbon atoms. Next is minus I effect. In case of minus I effect, if to the end of carbon chain, saturated carbon chain, there is a group which is electron withdrawing in nature. If electron withdrawing group is attached, examples of electron withdrawing groups are CHO group, COOH group, nitro group, etc. These are examples of electron withdrawing groups. So what this group will do? It will pull electrons from carbon chain to its side. So electron from carbon chain, they will start moving towards this atom. And as a result of this, this atom will get some negative charge. Since electrons move away from carbon chain, so the carbon atoms here, they will get some positive charge. Again, this factor will cease till the third carbon atom. This is observed only till the 3 carbon atoms only. So this kind of effect where electrons are displaced in a covalent bond in saturated carbon chain is called inductive effect. Now, next topic under this heading, electronic displacement in covalent bond after inductive effect is electromeric effect. Electromeric effect, and this one is represented by capital E. This is seen in case of unsaturated compounds where there is a multiple bond and there's complete transfer in this case of electrons. Like in case of inductive effect, there was partial movement of electrons. In this case, there is complete transfer of electrons of a multiple bond to one of the bonded atoms. Like for example, if we have this compound where there is a double bond, multiple bond here, and this shifting of electron, displacement of electron here of multiple bond towards one of these atoms, the one that is more electronegative electron will move towards that atom. So this movement will be only if in this reaction some reagent is added. In presence of this reagent only, what will happen? There is a double bond, one is sigma, one is pi bond. Pi bond can completely move towards more electronegative atom. So when this pi bond will move here, this O will get complete negative charge and carbon here will get complete positive charge because there's complete transfer of electrons here on this O atom, since O is more electronegative in nature. And this factor is seen only when there is an attacking reagent. Reagent is added, then only this effect is seen. That means this one is temporary in nature. Temporary means if we remove this reagent, then we will not see this transfer electron. It will come back to this form only. So reagent remove, it will come back. So this is temporary in nature. This can take place only in presence of an attacking reagent. This further is of two types, that is plus E effect and minus E effect. In case of plus E effect, like I'm taking this compound carbonyl, there is H plus reagent that is added. Positively charged reagent is added. Now O is more electronegative. Electrons of pi bond, they are moved to this oxygen. And as a result of this, we have done that carbon gets positive charge and this O gets negative charge. Negative charge oxygen is pulling this H plus. That means this H plus will attack this oxygen, because oxygen will have electrons and this is deficient in electrons, so this will attack this oxygen. So O negative and H plus, this becomes OH. Negative and positive charge will neutralize. This is called plus E effect. Why this is called plus E? Because electrons of pi bond are transferred to the atom to which the attacking reagent gets finally attached. The side where electrons are moving of pi bond, this attacking reagent is also attacking that side only. So that is why this is known as plus E effect. In case of minus E effect, electrons of pi bond move towards this oxygen when attacking reagent like Cn minus is added. Now electrons move on oxygen, so O gets negative charge and carbon gets positive charge. Now this is Cn minus. Minus will attack the positive side, so this will attack the carbon because carbon gets positive charge. So minus and positive, they will cancel, and now the attacking reagent is attacking the other side. Electrons are moving this side and attacking reagent links to the other side. This kind of effect is known as minus E effect. If the electrons of the double bond are transferred to an atom of the double bond other than the one to which the reagent gets finally attached, then this effect is known as minus E effect. So this is the second effect in this topic, electronic displacements in a covalent bond. Now next topic after this is resonance. This we have done in covalent bonding chapter also. So this is just the same, only resonance or mesomeric effect, also called mesomeric effect, and this is represented by capital R or by capital M also. And we have done, if one structure of a compound cannot explain all its properties, a single Lewis structure of a molecule cannot explain all its properties, then molecule can be represented by more structures if it's possible. Now what we'll do is, in the structure, this side will take single bond, this side will take a double bond. But none of these structures can explain all the properties of this molecule. And these possible structures that we have drawn, these are called resonating structures or canonical structures. These are called resonating structures or called canonical structures. An actual structure is in between all these possible structures that we have drawn and equivalent to this one, where there is no double or single bond. Both the bonds, they become of the same length, and these will be between the single and the double bond. This structure, actual one, is called resonance hybrid, and it's a most stable structure. So those compounds which show resonance means they are stable. All the possible structures written for a molecule are called canonical structures or resonating structures, and the actual structure is known as resonance hybrid. One more example for this. If I take sulfur trioxide, this is one double bond and two coordinate bond means single bonds are here. But there is no double or no single bond here. Another possible structure is we take this side double bond and this side we take single bond. But this also has the same problem. So another structure that we can draw is possible one is this side now we take a double bond. But all these structures cannot explain all the properties of sulfur trioxide. That is no double bond, no single bond. All three bond lengths are of equal length and are between the single and the double. So that actual structure is in between all these contributing structures where the pi bond character spreads little bit in the whole molecule, and this is known as resonance hybrid. So all three bond lengths becomes of the same length and between the single and the double one, and it's a more stable structure. Next one after this is the last topic under this one, electronic displacement, that is hyperconjugation. Hyperconjugation. Hyperconjugation, or also known as Baker-Nathan effect, and this is also known as no bond resonance. This is also called no bond resonance phenomenon also. So it's just like resonance only, a slight change here from resonance, no bond resonance. And this will be seen in unsaturated systems where there is when an alkyl group like CH3, I'm taking this side, alkyl group is attached to unsaturated system, the hyperconjugation takes place. So this is like resonance only, but if to the unsaturated part next to the unsaturated carbon atom, alkyl group is attached, then there is hyperconjugation. So it is an extension of resonance effect only. And in this case, delocalization of sigma electrons takes place. While in resonance, there is delocalization of pi electron, here delocalization of sigma electrons take place. Okay, so hyperconjugation in this case, if I am taking this compound CH here and CH2, what happens is this sigma bond of the alkyl group moves here, and because of this what will happen, this part will remain as it is. So I'm drawing the part where there is no change. Now when this is moving here, this one will become H plus because both the electrons are bond, they're shifting here, and now here we will have a double bond. In place of single bond, there will be a double bond. But this carbon will get 5 valency. So when these electrons are moving here, sigma electrons are moving here, this pi bond will come on this carbon and there will be negative charge now coming on this carbon. So this becomes single bond and CH2 minus will be here. But this H plus will not get time to move away because quickly this bond will shift here. Within fraction of second, this bond will shift here. So what will happen now? This H will link with the carbon now with this bond, and this H will become H plus. And now again this H plus will not get time to move away because this bond will shift here. And because of this, now there will be a bond between this hydrogen and carbon. No change in rest of the part, so I'm drawing it like this only. And this one here, this is hydrogen here. This one will be now H plus. This part will be H plus. So there are 1, 2, 3 and 4 structures that we'll get. So double-headed arrow between these structures that shows these structures are moving into each other. So H plus will not get time to move away from the compound here. Quickly this bond will come back here. This will move. So it will keep on moving like this only. So there is delocalization of sigma electron, single bond. Sigma electron delocalization is there. And because of this compound will become stable. But for the time being, fraction of second, there is no bond between two atoms. Between two atoms, no bond for fraction of second. That is why this is called no bond resonance. There is delocalization, resonance is there, but it is no bond resonance. This was given by Baker-Nathan. That is why this is called Baker-Nathan effect. And these structures, 1, 2, 3 and 4, these are called hyperconjugating structures. So in these structures, in 2, 3 and 4 structure, there is a free proton, H plus, H plus, H plus. Free proton is shown in the above structures, but it is still firmly attached and hence is not free to move. Hyperconjugation occurs through hydrogen atoms, and more are the number of alkyl groups attached here, more will be hyperconjugating structures and more is the stability. So this is about this topic in which we have done electronic displacements in a covalent bond.